Welcome everyone to today's event, Technology That Matters, Strategies to Precisely Control Synaptic Weights for Neuromorphic Computing Arrays, presented by SG Innovate and Singapore MIT Alliance for Research and Technology, or SMART. I am Zing from SG Innovate, and if you're new to us, we are a government-owned organization in Singapore with the mission to build deep tech innovations from Singapore for the world. We invest in and help build deep tech startups in the fields of artificial intelligence, medtech, and quantum tech, just to name a few. We work with entrepreneurial scientists and clinicians to help bring their innovative research from lab to market, and we also develop tech talent and engage with a vibrant deep tech ecosystem. Today, as part of our Technology That Matters series, SG Innovate and SMART are pleased to have Professor Kim Ji-won, MIT Department of Mechanical Engineering, today to bring you insightful knowledge on neuromorphic computing arrays. The event will be a presentation followed by a fireside chat. Just some house rules. During the webinar, if you have any questions, please post them in the Q&A box at the bottom of your screen. And do feel free to use the chat box to connect with our wider community. Before we have Professor Kim to start his presentation, let me hand over the time to Dr. Howard Califano, Director of SMART, who will be our moderator for the day, to say a few words. Howard, please.
Thank you, and welcome to Technology That Matters. This is the second in a series of webinars. If you attended our first webinar in September, welcome back. If this is your first talk with us, we'll be happy to have you here. This series is organized by SG Innovate and SMART, which is a Singapore MIT Alliance for Research and Technology. Our purpose is to help grow the Singapore ecosystem and to encourage deep insights and discussions in technology. And we have some extremely well-known MIT faculty members who will be sharing their research and their insights during this series. Our goal is to really open up networks of collaborations and opportunities. So please ask questions during the webinar, and I will convey those questions to our speaker. SMART is MIT's first and only research center outside of the United States. It's also MIT's largest international research program. We have MIT faculty members who come here and have laboratories, mentor postdoctoral fellows and graduate students, and collaborate with researchers from universities, research institutes, and industries in Singapore. Under the SMART umbrella, we have 5 research groups, and we have an innovation center, which is what I run. We provide grants throughout all of Singapore to all the institutions of higher learning to really provide new avenues for market-driven research, and also to help researchers and faculty accelerate their ideas in the lab and bring them to commercialization. We've launched 47 companies. In fact, we launched one last week, and we are very honored to be able to collaborate with SG Innovate to bring this program here to you today. So without further ado, I'd like to start off the event today by introducing Professor Kim Ji-won. Kim Ji-won is Associate Professor at MIT in Mechanical Engineering and Material Science and Engineering. Kim's group focuses on innovation in nanotechnology for next generation computing and electronics. Before joining MIT in 2015, he was a research staff member at the IBM T.J. Watson Research Center in Yorktown Heights, New York. He's received quite a number of awards. The Master Inventor at IBM, the DARPA Young Faculty Award, MIT IBM Faculty Award, the Lam Research Foundation Award, and he's a prolific inventor, having filed and having issued over 200 US patents, and has been the author of 50 articles in journals. So I'm very excited to now turn it over to Ji-won for him to give us his talk. Thank you. Ji-won?
All right, Howard, thank you so much for the nice introduction. And I appreciate to the SMART and SG Innovate to give me this prestigious opportunity to interact with people in Singapore, after the pandemic, worlds gets much closer because you don't even expect to have a, on-site seminar. It's becoming the new normal for us to have the this kind of Zoom type of webinar and seminar. So worlds gets closer, and if it's not a pandemic situation, I suppose to go to Singapore to give a talk, which takes 16 hours of a flight. 16, if I have to take the transit, it's going to be around 20 hours. So it's going to be painful, but it's good to have this kind of webinar through the Zoom. So thank you so much for this opportunity, and I hope you enjoy my talk today. I'll try to make sure that everybody are entertained with my talk. Okay, so let me start sharing my slide. All right. So can you see my slide? Can you guys see my slide, panelists?
Yes, we can.
Okay, so today I'm going to talk about the strategies to precisely control the synaptic weight for neuromorphic computing arrays. What does this synaptic weight means? Today I'm going to talk about the artificial intelligence hardware that my group at MIT is developing. So in order to have the precise AI computing task, you will need to have some control, precise control on the weight in artificial synapse arrays in neuromorphic computer. Okay, today I'm going to talk about the strategy that we have invented at MIT to control the synaptic weight to have a accurate pattern recognition by doing the neuromorphic computing. Okay, so to discuss about that, we have to cover the some sort of trend of the community first. Okay, so let's talk about the artificial intelligence. Okay, let's talk about the one of the most popular event in the world, which is the game between human being and the supercomputer. So first pronounced event was, let me change the pointer. Pronounced event was the Jeopardy show in the United States. As you can see from here, IBM Watson supercomputer beat against human being who is the champion in the quiz. Okay, that time 2014, that time I was employee of IBM, and we have a free lunch because IBM supercomputer beat against human being for the Jeopardy show. And more recently, Google's AlphaGo won against human Go champion. All right, so let me ask you this here to everyone, is this really fair game? I would say it's not fair at all, because human being, what is the size of the brain of the human being? It's kind of like six inch wafer scale, right? 6-inch wafer scale. It's really, really small, but this small brain fought against humongous computing resources, supercomputers. Okay, so this supercomputer is seriously connected to each other. It has a very large size footprint, and it consumes tons of energies because it uses thousands of CPUs, hundreds of GPUs, which are seriously connected. So in order to make this CPU and GPU, how many wafers you need? You can imagine like hundreds of wafers you need. And this humongous computing resources won against human being. What's the big deal, right? Yeah, so here, I'd like to give you some, very simplified idea how to compare the human brain versus, computer chips, CMOS chips, okay? So let's discuss about human brain. If you if I go through this slide, you will have an understanding why this game is not fair at all. Okay, so human brain, let's look at this. Human brain has 10 to the 14 synapses and 10 to the 11 neurons. Okay, in order for us to operate these 10 to 14 synapses and 10 to 11 neuron, all you need to do is to have a one hamburger, right? To make a power 20 watts. All you need to have is 20 watts to operate the brain with the 10 to 14 synapses. Okay, now let's compare our human brain to CMOS chip. Okay, as you can see, CMOS chip typically contains 10 to the 9 transistors, okay, on the wafer. Then, in order to emulate the human brain, and especially in order to emulate single synapse in human brain, at least you will need to have 10 transistors, okay, to emulate, to represent one synapse in the brain. Then imagine how many CMOS chips are needed, right? So CMOS chip on the wafer equivalent to only 10 to the 8 synapses, 10 to the 5th neuron. Okay, then to operate 10 to the 14 synapses, you need to have a multiple CMOS chip, which requires the megawatt type of the power. Okay, a huge difference between human brain and CMOS chip in terms of power consumption. Okay, we all know that. So, okay, it's okay to emulate the human brain by combining multiple CMOS, multiple transistors. Okay, we can have arrays of, artificial synapses by combining transistors, millions of transistors. Okay, this is not efficient. Then, can you emulate the one synaptic behavior, synapse behavior from one synapse, from one device? Answer is yes. This concept has been very long time. So we call it as a memristor. We call this device as a memristor. So this memristor device can work like the human synapse. One memristor can do the one synapse, what one synapse can do. Okay, so if we can apply the device called memristor as an artificial synapse, there's a possibility that we can do the AI task with a very, very low power consumption. Okay, so let's discuss about the memristor. What is memristor? Why memristor is so promising for the low power consumption AI task? Okay, so again, memristor, one memristor can do one synapse. The reason for this argument is because of as following. Okay, so in one memristor, you can register the multi-value of conductance in one memristor. So by applying some voltage pulse into the memristor, you can update your conductance level inside the memristor, which is equivalent to the synaptic weight. Okay, if you apply the positive bias pulse, you can continuously register the different levels of conductance value. If you keep applying the positive bias, you can enhance the conductance value in your memristor. On the other hand, if you apply the negative bias into your memristor, then you can reduce the conductance level. So you can switch back and forth of the specific value of conductance level in memristor, which is very similar to what synapse does. In synapse, it can change its weight up and down, which is called the potentiation and depression. So you can do the potentiation depression in one memristor. That's why one memristor can do one synapse. This is a source of saving tons of powers for AI task. Okay. So let's discuss about the switching mechanisms in memristor device. To do so, we need to have some understanding in materials, okay? Typically, people have been using the amorphous material as a switching medium. What does amorphous do? In amorphous material, there are tons of defect in it. Especially there are tons of vacancies. Okay. Through these vacancies, we can send through the positive ions or negative ions. In this specific example, I have drawn the positive ion movement through the defect in amorphous switching medium. So this amorphous switching medium is also called a solid electrolyte. So through the defect in the solid electrolyte, you can send the metal ions through. So if you completely send the metal from the top to the bottom, it makes a short state, it makes on state. Okay. If you apply the negative bias, you can disconnect this filament. So you make off state. So then how can you make this kind of analog potentiation depression behavior? Okay, it's very simple. You just apply the bias once with a very short pulse. You can make a filament. If you do it again, then your filament become thicker by adding more positive ions in this specific case. If you apply more, your filament gets thicker by receiving more ions onto the filament. That is how you make the analog state, like a human brain, human synapse. By applying the negative bias pulse, you can reduce the thickness of this filament, you can reduce the conductance, you can change the weight in the artificial synapses, which is a memristor, okay? So this concept is very sexy, and this can revolutionize the AI hardware, okay? But this story so far is very perfect, but there exist inherent problems in this memristor so far, okay? What is the problem? The biggest problem is coming from the randomness of switching due to the unstable filament. Why this filament is unstable? It's because this filament is randomly formed through the random amorphous switching medium. So random amorphous solid means already stochastic behavior of atomic movement inside. So it's really hard to control inside. That is why, in reality, if you switch, if you potentiate, if you depress your memristor device, it's not perfectly linear, it's not perfectly reproducible. Whenever you do this, you see the different potentiation and depression. This is a very typical problem. Not only that, if you apply the bias to make a filament, typically in conducting bridge RAM, we typically send the silver atoms through the switching medium, okay? If you do that, this filament, once you form the filament, this filament typically not very stable, especially if this filament is ultra thin. Because if your filament is very, very thin, then your surface energy is dominating compared to the bulk energy. So there is a strong tendency for this filament can be dissociated. Okay, if your filaments get thicker, it can be kind of stabilized because surface to volume ratio is reduced. You can see this behavior here. If your initial conductance is very low, if you wait for a long time, then your weight, your conductance suddenly drops and lose its memory, right? If you applied the more bias, so your initial conductance state is very high, then decay is much less. So this is the problem, because in order to have accurate recognition task by AI hardware, you will need to register the synaptic weight value, and this value needs to be constant, needs to be maintained. But in reality, this is not happening. So in order to have accurate AI task by using memristor, you will really need to find the material solution. to solve this problem, okay? Okay, so there is another solution other than material to solve this problem, which is easier somehow. So if the control of this weight is that difficult, why don't you just put down the transistor right next to the memristor, which is called the 1T1R technology. If you put one transistor right next to the one memristor memregister, you can have excellent control of potentiation and depression, okay? However, you need to have additional lines because now this operation is three-terminal operation. It's not simple two-terminal operation anymore, okay? So there is some burden in circuitry. There's some circuitry overhead for this, okay? So transistor can offer the weight control and linear and symmetric update, but still there's some burden in the circuitry, okay? So my group has been focusing on finding a way to operate the memristor array without having any transistor, as you can see here. This is showing the neuromorphic computing landscape. So this is kind of a full summary of what I have just mentioned. So supercomputer, of course, technological maturity is very, very high as far as you have the software for AI operation. You can just run it through this supercomputer. So technical maturity is pretty high, but ideality for the AI task is low because it has a very high power consumption and very large footprint is needed. And computing speed is less than just the computing speed ideally done by neuromorphic computing arrays. Okay, intermediate solution is a CMOS based. CMOS based is synapses, but still, the power consumption is much higher. So intermediate solution for this is to use the transistor right next to the register, mem register, to have the stable operation. So my group has been working on the 1R memristor array solutions. To do so, without using the circuitry solution, we really need to find the material solution, okay? So here, let me introduce our approach to tackle this problem, okay? Instead of using circuitry solution, we try to borrow the material solution that has been used for the metallurgy to strengthen the materials, okay? So far, what kind of metallurgical strategy exists to strengthen the structural materials? So you may know, if you're a material scientist, you may know these 4 kinds of strengthening mechanism. One is solid solution hardening, work hardening, and the grain boundary hardening and precipitation hardening. They're all, to make some interaction between the bulk matrix atoms and some precipitation and some solid solution, solute atoms, and some defect inside the material. That way, you can reduce the movement of dislocation so that you can harden the materials. So this is all about the interaction between the solute atoms and bulk matrix, interaction between the solute atoms and alloying element, and interaction between the atoms and the defect, okay? So we borrow this concept to have extra control on synaptic weight in the AI hardware, okay? We have been using the very traditional method in material science. Okay, first have a look at this. Like structural material guys have done, we try to mimic this strategy to have a control in memristor. First strategy we have used is the alloying conduction channels. Like I just mentioned, inside the switching medium, we form the conduction channel. And I just mentioned that conduction channel is very, very unstable. So we try to put some alloying element to stabilize these mobile metal atoms inside the memristor. Okay, that is the first strategy. okay, borrowed from the metallurgical solution. Another solution is to have the ion transport through the line defect inside the memristor, okay? So we, instead of using the amorphous switching medium, we try to use a single crystalline as a switching medium where there is excellent line defect, which is aligned from the top to the bottom, which is called the dislocation. So we try to make some interaction between these mobile atoms with this line defect, which is dislocation, so then we can have the control in ionic movement. These two strategies are not new in material science and metallurgical community. If you look at this book, published in 1964 or something, this already said some sort of solution for it, okay? One of the important thing is, by doing alloying, you can change it, the bonding properties of the metal ions inside, okay? And also, this book shows that if there exists dislocation pipe in the single crystalline solid, then this dislocation pipe becomes a selective path of moving the ions. So if you can have single crystalline matrix with this line dislocation, you can confine the ionic movement inside the dislocation. So we apply these two. We were interested in developing these two concepts to have extra control, okay, on the synaptic rate in the memristor. Let me first introduce our first strategy, which is alloying the switching metals. Okay, first, we have chosen the single crystalline silicon as our switching material, our memristor material. Okay, reason is that silicon is abundant, and the CMOS fabrication, CMOS fab, all CMOS fab is made out of silicon. So there is already infrastructure for silicon. So we just try to use silicon as a basic building block. Then we first try to find the mobile metals which can switch back and forth from the top to the bottom of the silicon, okay? So the condition for doing this is that the metal needs to freely move around inside the silicon, right? To do so, this metal does not like to form the compound with the silicon, because if this metal forms a compound with silicon, then it will form very stable compound with the silicon. It cannot be associated, no, it cannot be dissociated, meaning that you cannot reset this device, okay? Then what kind of metal is perfect for that? Perfect metal is the metal that does not have any solid solubility with the silicon each other, meaning that this material does not like each other, okay? Perfect material for that was silver, because as you can see from this phase diagram, silver has no solid solubility in silicon, and silicon does not have solid solubility in silver, meaning that silver attachment to silicon is very weak. That way, silver can freely move around to form the filament and to be a skinnier filament, to be a thickened filament. Okay. So for that sense, all this copper, nickel, chrome, tie is not a good mobile metals, because it will form the silicide compound, line compound. So we cannot use this. However, this line compound material is perfect for the alloying metals. Reason is that silver forms very weak interface with the silicon, so it can freely move around. That is becoming the source of the problem of having the non-uniform switching. So we can add a little bit of this compound forming metals to form the some sort of bridge between the unstable silver and silicon interface. Okay, these silicated metal forms the very stable interface with the silicon. Okay, so alloying metals was a candidate. It has to be reactive to silicon. Okay, not only that, this metal has to be immiscible to mobile atoms, meaning that this alloying metal needs to like a silicon. At the same time, this alloying metal needs to like the silver as well. All right. As you can see here, this is a typo. Sorry, this is a typo. As you can see here, copper and titanium likes each other. There's a solid solubility. Okay. However, nickel silver, chrome silver, they do not like each other because there's no solid solubility. So this nickel and chrome cannot be the alloying metals, but thermodynamically, copper and ti can be the good interface material. Okay. So to summarize, we have chosen the silver as a mobile metal, which is perfect to the switching medium, silicon switching medium, and we have chosen the silicated metal that has the good interaction with the silver and good interaction with the silicon. Okay, so thermodynamic selection is silver for mobile metals and copper ti for alloying metals. However, we also need to consider the kinetics. As you can see here, diffusivity of titanium and diffusion barrier of titanium is much higher than silver, meaning that even if you dope the titanium, you alloy the titanium with the silver, titanium is not moving faster than silver, so alloying effect is not very, very high. So now we screen out the ti, so copper is perfect candidate. By just following this material logic, we're able to successfully found the excellent alloying element to have excellent neuromorphic computing. Please see below. This is the switching behavior of the silicon memory, so with the different metals. As you can easily imagine, if you use a compound formation metal, there's no switching at all because copper, nickel, chrome, ti forms a silicide, very stable silicide. Once it's formed, it cannot be reset because it's very stable. So this is not going to be the solution again. Then if you use the silver, you have a switching, but unstable and very unreliable switching. At the same time, silver, as you can see, the long-term memory is not secured in multiple weight levels. Okay, so now we try to find the right copper contents to make an impact. As you can see here, in certain copper ratio, we are able to find the excellent switching behavior with long-term memory. Okay, so in the ideal alloying ratio, we make a clear difference between the pure silver device and alloyed device, as you can see here. Okay, so if you do the DC switching of silver-based silicon memristor, variation is quite high. But by putting a little bit of copper into it, we completely change the switching scheme. Then this statistics show that the silver copper alloy device has a very low variation, as you can see here. Not only that, it can also stabilize the filament, so we obtain the long-term memory in every different weight. So dramatic improvement has been observed by simply adding the copper. Okay, the story is very simple, but to find, like I just mentioned, we spend a long time to find this copper as an alloying element. Then our switching scheme is breakthrough. It's totally different from the conventional, unalloyed memristors. Okay. So what is the switching behavior with a different, alloying element? Okay, except for the copper, as you can see, if you add a titanium into silver, switching behavior is not different as just a silver device. Reason is that ti does not diffuse inside the switching medium faster than silver. So silver is dominating here. Okay, and chrome and nickel does not like the silver, so switching behavior is also kind of random. Okay, so copper really works well for this. And also silver copper alloyed RAM shows excellent analog switching behavior as well. As you can see here, silver copper shows linear and symmetrical behavior compared to the pure silver device, which is crucial to have excellent analog neuromorphic computing. Okay, you see the silver copper device shows repeatedly the symmetrical potentiation and diffraction behavior, as you can see here. With this, we are so encouraged to make the arrays, which is 32 by 32 sized arrays. And with this array, we are able to do some inference task. And as you can see, first we try to update the grayscale images on the memristor arrays. So 256 level grayscale images were updated onto this device. Again, as you can see here, this updated image is decaying for pure silver and nickel silver device, but silver copper device, it retains the updated image for a long time, which is simply because we have excellent alloying behavior into this silver copper based alloy RAM. Then we also have done some inference test, which is a convolutional kernel processing. So we did some kernel processing 3x3 matrix. Then we run it through our memristor. So we are able to process the image. We are able to sharpen the Killian court image. We are able to sharpen. We are able to soften. We are able to edge and vertical and horizontal. We can process image. This shows this memristor kind of works in a controllable manner, even without having transistor. Okay. And let me introduce another strategy that we have been using in our lab. So another strategy that we have used is to apply the dislocation inside the switching medium. Okay, so this mechanism has been already discussed. So if there is the dislocation in the solid, then this will be the preparation path. So we have grown the silicon germanium on silicon, where there is the threading dislocation, which is vertically aligned from top to the bottom, where you can combine the metal ions inside this dislocation. Okay, so as you can see, if we do not have any silicon germanium with dislocation, switching behavior is not observed. But by growing the relaxed silicon germanium on silicon, we are able to have a switching. And this switching behavior is extremely stable, and variation very, very low. But the on-off ratio is kind of low, so we also did some treatment where the etchant can widen up the top part of dislocation. Then we are able to get the higher on-off ratio as well. So this kind of dislocation engineering can have high on-off ratio memristor with excellent uniformity and excellent, spatial uniformity and temporal uniformity. Okay, so now, so far, I have introduced my lab strategy to control the weight in the 1R arrays, neuromorphic computing arrays, without having any transistor. But still, 1T1R shows a much better controllability. Of course, we use the transistor. So there's still a long way to go, but we are making progress towards having the precise control of synaptic weight inside the neuromorphic computing arrays made purely out of the memristors. Okay, so this is kind of like my group's direction on neuromorphic computing. So like I just mentioned, we are going to continuously improve analog switching behavior by finding further metallurgical solution. So far, it was so successful to find the right solution for metallurgy. So we still need to have a longer retention in multi-state. We still need to have more precise control of the multi-state weight. And also, we are super interested in forming the bioprocessable memristors. Typically, artificial neural network task, deep neural network task, long retention is needed in multi-state. However, sort of like a bioprocessable operation, you will need to have control of decaying time. So you need to have some decay in the weight. Okay, So we strongly believe that by changing the alloying element, we can control the decaying time. So we are working on this direction as well. And also, we are super interested in working on three-dimensional neural computing arrays because it allows us to do the high density memory registers, and by having the planar operation. Okay, so you have the plain wire instead of the line wire. You can reduce the resistance a lot, and also you can update the weight by directly printing the image. You don't have to unfold your image to have the one-dimensional input. Now you have a two-dimensional input, so you can just directly process the image to the neural computing arrays. So at the same time, my group is working on hetero-integration of this neural computing chip with other freestanding semiconductors. One good example is once you have a neural computing array, you really want to have the peripheral analog circuits for a hyper amplifier with a small footprint. Also, we wish to have some wireless communication of this neural computing chip with the external environment. And if we can have 3, 5 sensors connected to these neural computing arrays, you can have a kind of like a direct inference onto this neural computing arrays. So hetero integration is becoming more important in this direction as well. Okay, so my group, another part of my group has been actively working on the hetero integration solution. So my group has invented a way to make a freestanding compound materials by using the technique called the remote epitaxy, where you can have the continuously have the very thin, ultra flexible, stackable single crystalline membranes out of the wafer. Okay, so I'm very excited to introduce technology for hetero integrating with neuromorphic computing chips. Okay, so to summarize, again, metallurgy concept could resolve the issue. We are very excited about that. So we are going to continuously explore the metallurgical solution to take care of the problems in AI hardware community based on the memory cell. Okay, thank you so much for your attention. And I really have to credit to my student and postdoc who allow us to make this excellent progress so far. Thank you so much.
Professor Kim, thank you for the wonderful talk. We're going to have a little fireside chat now, okay. and then we're open to questions too. So please send your questions to us, and I'll convey those to Professor Kim. Let me ask the first question. We've seen the digital circuitry progress from CPUs, GPUs, field programmable gate arrays, ASIC chips. And now it looks like the next step is neuromorphic chips, particularly since Moore's law is ending and the possibility of shrinking transistors is fairly low now. Where do you, looking ahead, what advantages do you see that neuromorphic chips are going to be able to provide us?
Yeah, so because very simple and easiest answer is this supercomputer is not carryable, right? So it's not portable. So by having this low power consumption, low footprint, memristor-based neural computing chips, you can carry this supercomputer, right? That is the ultimate goal, but it's still the long way to go. Like I just mentioned, you cannot completely control this synaptic weight, okay?
Correct.
So intermediate solution will be edge computing. You use small scale neural computing arrays to do some computing at the edges. Okay, so that can be the intermediate solution, right?
So I noticed that True North, which is the neuromorphic chip that MIT, IBM, excuse me.
IBM, yeah.
IBM has developed, only draws about 70 milliwatts. How is this lower power achieved? And again, what is the implication commercially for being able to do this level of computing power with such a lower electrical power consumption?
For true north, right? True north.
True north.
Yeah. So obviously the functionality is limited. The size of the arrays is not very large, and on the other hand, it shows the almost first shows the concept of neural computing. Even if you use bundles of transistors as a synapse, they show that this is the way to go by using the CMOS chips. So this is very valuable approach. And actually, in this landscape, if we can achieve the very stable operation of memories, that this could be the winner in a way that there is the low power consumption and can compare to CMOS chip. Okay, but in CMOS chip, right now, as far as I believe, right now the solution to realize the CMOS-based synapses is based on defining the algorithm and the way to operate the CMOS chip with a very low power consumption. For example, like instead of doing artificial neural network, deep neural network, you can do the SNN, spiking neural network, and it can be wired in when it's necessary. So there is some other algorithmic solution to reduce the power on this. So each technical node, eventually we don't know what's going to be the final, perfect, AI hardware. But each technical sector making its own progress so far. Like I mentioned, progress is slowest here because it's most difficult. Okay.
Right.
Yeah.
So you had mentioned before that the commercial application for a neuromorphic chip would probably be more edge computing. Could you elaborate on that a little bit, and when you think these chips would start being able to be on the market?
The market, yeah, that's to me a hard question to answer, but you can ask it later to the Intel guys and IBM guy that develops the Rohi chip and the True North. But anyways, the time to commercialize the small scale arrays for edge computing will be much shorter, and you can put the small scale arrays to do some direct inference task on site. So it can be much quicker than the large scale operation.
Very good.
Yeah.
So we have a couple of questions coming in. They're extremely technical. So let me just read them.
Yep.
One says the background off-state leakage current seems to be higher in the silver-based RRAM. Any strategies to reduce power consumption?
So could you read the question again?
Yeah, the background off-state leakage current seems to be higher in the silver-based RRAM. Any strategies to reduce power consumption?
Oh, so we are, I didn't add the slide here. We are kind of putting the Schottky barrier. For us, we've tried to put the, Schottky barrier on the silicon. We try to dope the silicon, so then we try to make some selector in it. So then we can reduce the, the cynic path by putting the, natural Schottky barrier inside, because we are making a junction between the silver copper and the silicon. So we do some p-type doping in silicon. We try to alter the doping level to have a Schottky barrier to use as a selector.
Very good. Hope that answered the question. And we're getting a lot of questions about, again, use of neuromorphic computing. we talked about computing on the edge computing, which I guess would be, self-driving cars, image recognition, robotics. You did mention something which is close to our heart, is heterogeneous integrated chips, because certainly here at SMART, we're putting 3.5 material on CMOS, so we can get both digital and analog circuits. And so I guess a heterogeneous integrated chip would have both 3.5 material analog circuits, communication circuits, switching circuits, as well as the neuromorphic chip. Run your imagination on that, and also look at the different applications that could come out, and how do you see that evolving over time?
Still at the moment to us, it's kind of a dream, right? You put you put the material that you want, like a sticker. Okay, we made the basis for doing this. As you can see, you see this. This all single crystalline 3,5 and 3 nitride and complex oxide are all thin on the tape is ready to be stacked. Okay. Still, you will need to avoid some cracking and mechanical defect by doing some stacking process, but eventually this will enable us to heterointegrate all them together. As an intermediate demonstration, we try to put some laser or LEDs as the output line of this neural computing arrays. Then we try to put the photodetector as the input line. So then we can build up the photodetector. This is an example, okay, that we are developing. We put the photodetector and neural computing arrays and light emitter, which can be or laser. Okay, then this one unit can be stacked. So then you can have alteration, right? So LED and photodetector communication, you can stack up like a Lego block. By doing so, you can actually enlarge the size of the arrays. So this is kind of like one example of the excellent example of utilizing heterointegration to impact on the neuromorphic computing hardware.
Oh, okay.
Is it clear to you?
Yeah. No, that'd be very good.
They're all like remote texture ground on 3.5 wafer. We peel off from the wafer, then we just stack up on the neuromorphic computing arrays.
So let me ask a kind of follow-on question. We were talking about this earlier about how you would, once you completely stabilize the synaptic switch as you desire, and you get the correct, and you want to start putting it in silicon. I understand that you're able to fabricate these on normal silicon wafers. So do you envision that this is something that could fit into a normal CMOS foundry, or are you going to have to come up with a new fabrication tools?
Yeah, our chip itself is very simple. It was just put the alloying metals on the silicon wafer with some doped silicon wafer. So we grow p-type doped silicon layer on top of p++ silicon. Then we put down the metals. So this is completely CMOS compatible. But one problem that we couldn't solve so far is that the not avoiding silver. Silver is not ideal to be to go onto the front end of the line. So it is BEOL compatible, but not FEOL compatible. So we are actively looking for the other metal that can be compatible with the existing front end of the line.
Very good. Now you also mentioned the germanium silicon dislocation as a process. Well, could you clarify what the advantages of that would be as far as making the synapse stable?
Oh, okay. So yeah, I spend more time on the alloying because this is our most recent work. This is already quite old work, but anyways, the principle is that, as I mentioned, As you can see, switching medium used to be the amorphous. So ionic movement is very random inside. So we try to use the single crystalline as a switching medium. Instead of putting a lot of vacancies and defect, we just align the one line defect so that you can confine your metal ions inside these lines. Right? Does it make sense?
Mm.
That way you can have control over switching. Okay.
Very good.
All right.
So there are a couple of other questions that are coming up. One is a fairly technical question. Looking at the kinetic selection topic, and asking the question of does copper, using copper as one of the alloys, does that affect the ease of reset, the switching or dispensation of silver during the reset?
Yeah. That's a good question. So that's why if you have too much copper, it's hard to be reset. Too much copper. Okay. So there is the ideal composition. Okay. So the first author of this paper, Dr. Yan, found the right amount to have an excellent reset, excellent, long-term memory. Yeah.
Very good.
So there's a small window that you can use to have a good reset of the device. Okay.
Yeah, there's been several questions coming out, just understanding what is the right ratio of silver and copper. How much silver, how much copper do you put into the silicon?
So this is ideal.
Narrow window that you're looking at.
Yeah. So this window. So nominal thickness of silver, aim thickness was 2 nanometer, and in the copper was 1 to 2 nanometer. Within the range, we can have good switching.
Very good. We have one question that's a little bit more basic of a question, going back to what do you do? How do you define MEM resistor? I know that traditional circuits are on off, binary, and a MEM resistor is part of the synapse connecting the different neurons. But how would you define for our audience MEM resistor, which is what you're focusing on?
Yeah, so literally memory plus register. So this two-terminal register is a two-terminal, right? This two-terminal register can work as a memory. That's a MEM resistor, right? So as I have shown here, by having the certain thickness of filament from top to the bottom, it memorizes its conductance state in this two-terminal register. Okay. Then this conductance level can be tuned by changing the number of pulses applied to this two-terminal register. Then the memory characteristic will be changed. It can alter its initial state of the conductance. Okay.
Very good. There's one question, and I know that when you started, you were talking about the filaments, and now you talked about doping and then boundaries and that sort of stuff. So the question is what you observe experimentally in the switching mechanism, is it still a filament, or is it kind of a bulk switching?
Yeah, I wish I could answer this completely. We are working on it still. Okay, we explain this based on our best knowledge, our best understanding of the device behavior. So materialistically, we are still investigating on it. It's kind of hard to see the very thin filament, and it's very hard to hunt for it. And yeah, we are still looking for the answer for this. Yeah.
And another question was, to get to the off state, you have to completely break or dissolve the filament, or can you have?
No, you just simply disconnect at some location. That's the widely accepted theory for the reset.
Very good. I guess, was just have a kind of a last question that I have, and it's kind of one of those kind of crystal ball questions. But I was reading in Nature just yesterday about a group of neuroscientists who were looking at just a portion of the fly brain, a portion that had about 25,000 neurons and about 20 million connections. And using AI and better microscope technology, they were able to figure out all the connections and all that. So you have, on one side of the world, you have the neuroscientists, people like at the Allen Institute and all that are looking at the biological brain from a connectivity perspective. And you're looking at how to make more better neurons and synapses at the other end, looking at material science and engineering and those sort of things. And it seems like there's an interesting potential convergence that's going to be happening. Once the neuromorphic chips are better, stable, switching cycles are stable. And once they understand the interconnectivity of all these synapses and neurons, it could create a very interesting, so looking, just from a crystal ball perspective of where do you see this going? Obviously, the first step is going to be, having a better edge computing, neuromorphic chips on the edge for image processing, whatever. But where do you see this thing can go? And just to inspire particularly the younger scientists and researchers and students that are joining us, as a leader in this field, where do you see this can go? And do you see more interdisciplinary interactions between biologists and neurologists and material scientists?
Exactly, that is the key to make a fast progress on this area, So even still between electrical engineers and material science, there's a huge gap, and there's a gap between the electrical engineers and the algorithm people in computer science. So this field cannot move forward, move fast without having the collaborative effort and constant communication among the different disciplines. For example, in order to make this kind of progress, my group has one material scientist, one circuit designer, one device physics guy, one algorithm guy. All these different fields needs to be harmonized together to make a fast progress on it. This is crucial to make an impact. Still, our work has a gap with the upper level people who develops the algorithms in computer science, and still the gap with the neuroscientists as well. So we have to continue to communicate.
So it's a kind of a brave new world going forward of collaboration, communication, interaction between all the disciplines to go to the next level, which may be general artificial intelligence. Who knows at some point? Well, very inspiring talk.
Thank you.
We really look at the future of occurring in these neuromorphic chips, and I noticed that the time is up. Unfortunately, there's many more questions that are coming in, but unfortunately, we have to end the webinar now. The session is going to be on YouTube, so you can go to our various websites and you can find it if you want to refer back to it. Prof. Kim can be available for further discussions. His email is going to be made available, so you can contact him and continue the discussions. And again, that's the purpose of this this webinar, is really to get people excited about topics and to start developing that networking and collaboration that we need in science for it to really progress, and for us to see, these huge potential commercial products that can come out of this. Well, Prof. Kim, again, thank you very much. For those of you, we invite you to come back next month, November 25th, where we'll have another webinar with Professor Marcelli from MIT, We'll be talking about wrapping food in silk to extend shelf life, talking about food sustainability and reducing food waste. So I hope you all enjoyed this Technology That Matters webinar. And Professor Kim, thank you very much again for the wonderful talk. Have a great morning, rest of the morning and afternoon, everyone. Thank you.
All right. Bye. Thank you.
Everyone. Bye-bye.